Beyond the familiar worlds of our solar system lies a frozen frontier so vast and unexplored, it makes the outer planets seem like close neighbors. The Kuiper Belt stretches billions of miles into the darkness, a shadowy realm of icy relics left over from the birth of our cosmic neighborhood. Here, far from the sun's warmth, strange objects drift in silence, some as ancient as time itself, others so bizarre they challenge everything we thought we knew about the origins of our solar system. And among them, 25 mysterious bodies stand out, each holding secrets that could rewrite the story of how our celestial home came to be. Picture a place where the sun is nothing more than a faint star in an endless black sky, where temperatures plunge so low that even the air we breathe would freeze solid in an instant. This is the Kuiper Belt, a graveyard of cosmic leftovers from the solar system's chaotic infancy. But hidden among these frozen wanderers are enigmas that refuse to fit the rules: objects with odd shapes, unexpected colors, and orbits so strange they shouldn't exist. Some might be fragments of long-lost planets, others could be visitors from even deeper space, and a few defy explanation entirely. What makes these 25 objects so special? Some glow brighter than they should, as if hiding unseen forces beneath their surfaces. Others move in ways that hint at unseen companions or tug from invisible cosmic giants. And then there are those that simply don't look like anything else we've ever found, uneven, jagged, or glowing with colors that shouldn't belong in the icy darkness. Every new discovery peels back another layer of mystery, revealing just how little we truly understand about the distant edges of our own celestial backyard. So buckle up, because today we're venturing into the deep freeze to uncover the strangest, most baffling inhabitants of the Kuiper Belt and the jaw-dropping clues they hold about where we all came from. The first stop on our journey through the Kuiper Belt's greatest mysteries brings us face to face with Arrokoth, an ancient relic so perfectly preserved it's like opening a time capsule from the solar system's earliest days. When NASA New Horizons spacecraft snapped the first close-up images of this bizarre object, scientists gasped. Instead of the rough, cratered surface they expected, Arrokoth looked like two cosmic pancakes gently pressed together, its two lobes fused in a delicate dance that defied conventional wisdom. This wasn't just another icy rock. It was a primordial masterpiece, untouched by the violent collisions that reshaped most objects in our solar system. What makes Arrokoth so extraordinary isn't just its unusual shape. Its surface is coated in organic molecules and methane ice, materials so pristine they've remained virtually unchanged for over 4 billion years. Think of it like finding a fossil frozen in perfect condition, giving us an unprecedented glimpse into the building blocks that eventually formed planets like Earth. And here's where the real mystery kicks in. Arrokoth's two lobes didn't smash together violently. They merged slowly, almost tenderly, like two snowflakes drifting into each other in zero gravity. That gentle union challenges everything we thought we knew about how planetesimals formed, suggesting the early solar system was far calmer and more cooperative than our previous models predicted. Yet for all we've learned, Arrokoth still holds onto its secrets. Why does one lobe appear smoother than the other? What hidden chemistry lurks beneath its reddish surface? And most intriguingly, are there more objects like it waiting to be discovered? Every answer New Horizons provided seemed to spark 3 new questions, proving that even in the frozen depths of the Kuiper Belt, the story of our cosmic origins is still being written. While Arrokoth showed us the gentle beginnings of our solar system, Haumea takes us into the realm of cosmic oddities with a twist no one saw coming. This egg-shaped dwarf planet spins so fast it should have torn itself apart, completing a full rotation in just under 4 hours, a dizzying pace that flings its icy surface outward like a figure skater pulling in their arms. But the real shocker came when astronomers discovered something they never expected to find in the Kuiper Belt. Haumea has its own ring system, a delicate halo of debris circling its waist like Saturn's famous rings shrunk down for the frozen outer solar system. What makes this ring so baffling isn't just its existence, but how it survives in such an extreme environment. Haumea's rapid spin should have scattered any loose material into space, yet somehow, this tenuous band of particles maintains perfect balance. Scientists suspect the ring might be the remains of a catastrophic collision, where another Kuiper Belt object smashed into Haumea with just the right angle and force to leave behind a debris field stable enough to persist for eons. Others theorize gravitational interactions with Haumea's two moons, Hioka and Namoka, could be shepherding the particles into place like celestial traffic cops. Then there's Haumea's surface, a mirror-bright expanse of crystalline water ice that gleams like a cosmic disco ball. Most objects in the Kuiper Belt collect layers of dark organic gunk over time, but Haumea's extreme spin might be constantly refreshing its surface, exposing fresh ice like a self-polishing gemstone. Add to that its bizarre, elongated shape, and you've got a world that looks more like a rugby ball than a planet, stretching the very definition of what a dwarf planet can be. The deeper mystery, Haumea's ring, challenges our understanding of where such features can form. Rings were supposed to be the exclusive domain of gas giants, sculpted by their immense gravity. Finding one around a small, rocky, icy body in the Kuiper Belt forces us to reconsider how common, or how strange, these cosmic accessories might really be. Could other dwarf planets have hidden rings? Are we looking at the shattered remains of lost worlds, or witnessing the birth of something entirely new? Every observation of Haumea peels back another layer of this icy enigma, proving that even in the solar system's quietest corners, nature still has surprises up its sleeve. Just when you thought the Kuiper Belt couldn't get stranger, Makemake throws us a cosmic curveball, mysterious bright spots that glitter against its otherwise dark surface like celestial headlights in the void. This reddish-brown dwarf planet, named after the creation deity of the Rapa Nui people, has patches so reflective they outshine freshly fallen snow on Earth. What could possibly be causing these dazzling anomalies on a world where temperatures hover around -240 degrees Celsius? One leading theory points to cryovolcanism, ice volcanoes spewing not lava, but a slushy mix of water, ammonia, and methane. If Makemake's interior retains even a whisper of heat from its formation, these cryovolcanoes could be erupting periodically, coating the surface with fresh, highly reflective ices. Imagine a geyser frozen mid-eruption, leaving behind a gleaming patchwork of frost brighter than anything else in its neighborhood. But here's the twist: Makemake shows no obvious signs of recent geological activity, no fissures or mounds typical of volcanic terrain. So if cryovolcanism is at work, it's happening in ways we've never seen before. Then there's the methane snow hypothesis. On Pluto, methane condenses directly into atmospheric snow, dusting its peaks like an otherworldly ski resort. Could Makemake's bright spots be similar regions where methane vapor freezes into crystalline powder, creating mirror-like plateaus? Spectroscopy reveals the patches are rich in methane ice, but their uneven distribution suggests something more complex at play. Why do they cluster in specific areas rather than spreading evenly? And why do some regions appear brighter than pure methane should allow? The wild card explanation. Exposed slabs of nitrogen ice hardened into glassy sheets over eons. When New Horizons visited Pluto, it discovered vast plains of nitrogen so smooth they reflected sunlight like celestial ice rinks. If Makemake once had a more substantial atmosphere, its escape could have left behind similar nitrogen deposits in isolated pockets, polished by micrometeorite impacts over billions of years. But perhaps the most tantalizing clue lies in what we don't see. Unlike Haumea or Pluto, Makemake has no known moons or rings, no obvious sources of gravitational disruption that could refresh its surface. So how does it maintain these brilliant features in an environment where cosmic radiation should have darkened them long ago? Whether it's hidden geology, exotic chemistry, or forces we haven't even imagined yet, Makemake's luminous puzzles remind us that even in the solar system's quietest corners, the universe still has a few magic tricks up its sleeve. Dancing through the frozen expanse of the Kuiper Belt like celestial partners locked in an eternal waltz, Orcus and Vanth present one of the most striking duos in the outer solar system. This isn't your typical dwarf planet with a tiny moon. Vanth, the companion, is nearly half the size of Orcus itself, making their partnership more like a cosmic brother and sister act than a parent-child relationship. Their synchronized orbit is so precise, it's as if an invisible tether connects them, each always showing the same face to the other as they glide through the darkness. What makes this binary pair so puzzling starts with their surfaces both cloaked in a deep reddish hue darker than dried blood, a telltale sign of complex organic molecules baked by eons of cosmic radiation. But here's the twist. While most Kuiper Belt objects share this rusty coloring, Orcus and Vanth's tones match too perfectly. Did they form together from the same primordial material, or was Vanth ripped from Orcus in some cataclysmic encounter? The leading theory suggests a colossal impact billions of years ago, when a rogue object slammed into a proto-Orcus, launching debris into orbit that eventually coalesced into Vanth. Yet the math doesn't quite add up. Vanth's sheer size would require an impact so violent it should have shattered both bodies entirely. Then there's the mystery of their compositions. Spectroscopic studies reveal both worlds are rich in water ice, but Vanth reflects significantly more sunlight than its larger partner. One explanation. Vanth's surface might be younger, refreshed by cryovolcanic activity or constant micrometeorite impacts churning up fresh ice. Or perhaps Orcus's darker tone comes from a thicker blanket of radiation-processed organics, suggesting it's been exposed to space far longer than its companion. The most tantalizing clue lies in their orbits. Most binary systems in the Kuiper Belt have wide, lopsided separations, but Orcus and Vanth circle each other at just 9,000 kilometers apart, close enough that an astronaut standing on Orcus could see Vanth's craters with the naked eye. This tight embrace hints at a turbulent past where gravitational interactions slowed their spins and reeled them inward like two dancers pulling closer as the music fades. Could Vanth have once been independent, captured by Orcus's gravity in a chance encounter? Or are we looking at the remnants of a shattered third body that once orbited between them? Every new observation peels back another layer of this frosty enigma, proving that even in the quietest corners of the solar system, the universe still knows how to throw a curveball. Quaoar should have been just another frozen world lost in the Kuiper Belt sea of darkness until astronomers spotted something orbiting it that defied every rule in the cosmic playbook. This dwarf planet, barely half the size of Pluto, somehow possesses a ring system that shouldn't exist, floating mysteriously far beyond what scientists call the Roche limit. That invisible boundary marks where a moon should be torn apart by tidal forces, yet Quaoar's ring dances well outside this danger zone, surviving against all odds like a defiant cosmic rebel. This discovery sent shockwaves through the astronomy community because rings aren't supposed to form or persist in such distant orbits. Around gas giants like Saturn, rings are sculpted by gravity within the Roche limit, where moons crumble into debris. But Quaoar's ring sits over 7 times farther out, a gossamer halo of ice and dust that survived billions of years without collapsing into a moon or dispersing into space. How? One radical theory suggests hidden shepherd moons, tiny, unseen bodies whose gravitational nudges keep the ring particles in check like invisible traffic cops. Yet even these hypothetical moons would struggle to explain the ring's razor-sharp edges. which resemble a freshly groomed racetrack rather than the chaotic scattering expected so far from its host world. The plot thickens when we examine Quaoar's own chaotic dance. Its rotation is unusually slow, hinting at a violent past where collisions or gravitational encounters might have left behind this improbable ring as collateral damage. Some researchers propose the particles could be remnants of a moon that ventured too close and was vaporized by tidal forces. But again, why hasn't this debris coalesced or drifted away? Even more perplexing is the ring's temperature. Unlike Saturn's icy rings, which sparkle with reflected sunlight, Quaoar's ring is oddly dark and cold, suggesting it's made of porous, fractal-like ice chunks that absorb rather than reflect light. This fluffiness could help the ring resist collapse as particles bounce off each other like cosmic popcorn instead of sticking together. What Quaoar reveals is a gap in our understanding of how delicate structures endure in the cosmos. If rings can exist outside the Roche limit, entire chapters of planetary science may need rewriting. Could other small Kuiper Belt objects harbor hidden rings? Are we seeing the ghosts of ancient collisions or the birth of new cosmic phenomena? This tiny world's defiance is a humbling reminder that even at the solar system's frozen edges, the universe still has rules waiting to be broken. When New Horizons revealed the first images of 2014 MU69, the entire astronomy community did a double take. Here was a cosmic snowman floating in the void, its two flattened lobes pressed together like celestial pancakes frozen in mid-collision. Officially nicknamed Arrokoth but forever etched in history as the Space Snowman, this bizarre object became the most primitive solar system body ever explored up close. Unlike the violent smash-ups that typically shape celestial objects, Arrokoth's lobes show no signs of trauma where they merged. Their contact point is eerily smooth, as if someone carefully welded two lumpy potatoes together in zero gravity. The real shock wasn't just its shape but its color, an astonishingly rich crimson deeper than a Martian sunset. Spectrometers revealed this ultra-red hue comes from complex organic molecules called tholins coating its surface like cosmic rust. These same compounds are thought to be precursors to life's building blocks, suggesting Arrokoth might be preserving primordial ingredients that once seeded Earth with organic material. Even more intriguing, the two lobes share nearly identical coloration despite likely forming millions of kilometers apart before their gentle rendezvous. How such fragile structures survived 4.5 billion years unscathed challenges all assumptions about the early solar system. Current models suggest Arrokoth formed when two separate icy bodies, born from the same swirling cloud of debris, spiraled toward each other at walking speed, their merger so delicate it wouldn't have cracked an eggshell. This slow-motion cosmic ballet implies the ancient Kuiper Belt was more Zen garden than demolition derby, with objects coalescing through gentle attraction rather than violent impact. Yet questions linger like shadows in the frozen dark. Why are both lobes so unusually flat? Some theorize eons of sublimation wore them down like sandpaper on wood, while others propose they formed from pancake-shaped clouds of pebbles collapsing under their own gravity. Then there's the mystery of Arrokoth's missing craters. Its surface is suspiciously smooth for something that old, hinting at unknown processes erasing impacts or perhaps even sporadic geologic activity in its distant past. Every new data download from New Horizons seems to peel back another layer, revealing that even the quietest corners of our solar system hold stories far stranger than fiction. Gong Gong cuts through the Kuiper Belt like a cosmic rogue, its orbit tilted at a jaw-dropping 30-degree angle, a renegade trajectory that sets it apart from the flat, orderly plane where most solar system objects reside. This crimson-hued dwarf planet doesn't just drift lazily through space. It carves a steep, looping path that suggests a violent past, as if some ancient gravitational kick sent it tumbling askew. What could have thrown a world over 900 miles wide so dramatically off course? One leading theory points to a close encounter with Neptune billions of years ago, where the ice giant's gravity might have acted like a celestial slingshot, hurling Gong into its peculiar dance. But the surprises don't stop there. Gong rotates at a glacial pace, taking nearly 22 hours to complete a single spin, unusually slow for a Kuiper Belt object of its size. This sluggish rotation hints at an invisible brakeman at work, possibly its moon Xiangliu, whose gravitational tug could be slowing Gong down like a cosmic paddle dragging through water. Yet Xiangliu itself is an enigma, orbiting chaotically rather than following a neat, circular path. This irregular motion suggests it might not be a primordial companion but a captured interloper, adding another layer of intrigue to Gong's backstory. Then there's the tantalizing possibility of what lies beneath. Gong's surface shows signs of fresh ice, a telltale glimmer that could indicate cryovolcanic activity or even a hidden subsurface ocean. Imagine a reservoir of liquid water kept from freezing by tidal heating or radioactive decay, sloshing beneath miles of ice in the solar system's deep freeze. If true, Gong would join Europa and Enceladus as a potential harbor for exotic chemistry, or perhaps even life's building blocks in the unlikeliest of places. The most baffling piece of the puzzle, Gong's vibrant red color, deeper than Mars and more intense than most Kuiper Belt objects. This hue likely comes from Tholen's complex organic molecules cooked up by eons of cosmic radiation bombarding methane ice. But here's the twist. Patches of Gong's surface appear significantly darker than others, as if something, maybe seasonal changes or ongoing geologic processes, is selectively erasing or refreshing its crimson stain. Could Gong's tilt, its sluggish spin, and its mysterious moon all be clues to a cataclysmic event that reshaped its destiny? Or are we seeing the fingerprints of forces we don't yet understand, acting over billions of years in the solar system's silent outskirts? Every observation peels back another layer, revealing that even in a realm of ice and darkness, the cosmos still knows how to keep us guessing. Hidden among the Kuiper Belt's icy wanderers lurks a dark giant that defies expectations 2007 or 10, a world so massive it rivals dwarf planets like Ceres, yet so elusive it slipped past astronomers' notice until well into the 21st century. Here's the cosmic irony. This reddish behemoth reflects more sunlight than Pluto's moon Charon, yet it remained invisible to telescopes for decades. How could something so bright stay hidden for so long? The answer lies in its agonizingly slow dance, a single rotation that takes nearly 45 hours, the longest spin of any large object in the Kuiper Belt. This sluggish turn means its surface reflects light inconsistently, like a dimming lighthouse beam, making it easy to overlook in wide-field surveys designed to catch faster-moving targets. Then there's the puzzle of its color, a deep, rusty red that stains the icy surface like dried blood. Spectroscopy reveals this hue comes from Tholen's complex organic molecules created when methane ice gets bombarded by cosmic radiation over billions of years. But 2007 or 10 redness is unusually intense, even for the Kuiper Belt, suggesting its surface chemistry has been cooking longer than most of its neighbors. Some researchers speculate its slow rotation plays a role here too. With each day lasting nearly 2 Earth days, one hemisphere bakes continuously under the faint sunlight while the other lingers in prolonged darkness, creating a lopsided chemical factory where reactions unfold at a glacial pace. The real shocker, this world might be hiding water. Despite its dark appearance, patches of 2007 or 10 surface show spectral fingerprints of pure water ice puzzlingly bright against the reddish backdrop. One theory suggests cryovolcanic eruptions periodically resurface areas, blasting fresh ice from the interior like a cosmic pressure cooker. Another possibility involves impacts churning up buried layers, exposing pristine material to the void. But with no spacecraft visits planned, these gleaming patches remain silent enigmas. their origins debated in scientific papers. Perhaps the most humbling lesson 2007 or 10 offers is how much we still don't know about our own cosmic backyard. Even in an age of high-resolution telescopes and interplanetary probes, the Kuiper Belt keeps surprising us, proving that sometimes the biggest mysteries aren't the faintest objects, but the ones hiding in plain sight, moving to rhythms we're only beginning to understand. Eris gleams in the distant reaches of the Kuiper Belt like a shattered mirror reflecting scattered sunlight, its surface a chaotic mosaic of dark plains and dazzling bright spots that create one of the most extreme albedo contrasts ever seen in our solar system. While Pluto's famous heart-shaped glacier steals the spotlight, Eris boasts its own enigmatic feature, a sprawling, irregular patch near its equator that outshines fresh snow on Earth. This isn't just another icy plain, it's a glaring anomaly that radiates almost twice as much light as its surroundings, a beacon in the darkness that defies easy explanation. What makes this bright region so baffling isn't just its intensity, but its composition. Spectroscopic analysis reveals it's dominated by nearly pure methane ice, frozen into an exotic crystalline structure unlike anything found on Pluto. On its smaller neighbor, methane mixes with nitrogen and carbon monoxide, softening its reflectivity. But Eris's methane exists in a startlingly pure form, its surface so untainted by other ices or organic gunk that it acts like a celestial hall of mirrors. Some researchers propose the methane here undergoes seasonal sublimation, rising as vapor during Eris's closest approach to the sun before snowing back down in ultra-reflective patches. Others suspect cryovolcanic vents might be spewing fresh methane onto the surface like a cosmic frost machine. The plot thickens when we compare Eris to Pluto. Both worlds have nitrogen and methane, but Pluto's volatile ices flow in massive glaciers, while Eris's cling stubbornly to highlands like frost on a mountain peak. This stark difference hints at Eris's bizarre thermal history. Its subsurface may lack the slushy, mobile layers that shape Pluto's geology, instead remaining frozen solid for billions of years. Yet the bright spot's sharp edges suggest something is actively maintaining its boundaries, preventing the methane from dispersing evenly across the surface. Could residual heat from radioactive decay be creating microclimates beneath the ice? Or are we seeing the aftermath of a colossal impact that excavated pristine methane from deep below? Then there's the wildcard theory, tidal heating from Eris's moon Dysnomia. Though tiny compared to its parent body, Dysnomia's gravitational tug might generate just enough friction to keep isolated pockets of Eris's interior slightly warm, allowing methane to occasionally bubble up through cracks in the ice. It's a long shot, but in the Kuiper Belt, where conventional rules often fail, even improbable ideas deserve consideration. The real lesson Eris teaches us is that dwarf planets aren't just smaller versions of planets, they're entire new categories of worlds with their own rules. While Pluto remodels itself with shifting glaciers and nitrogen winds, Eris stands as a frozen vault, preserving ancient ices in conditions so extreme they challenge our definitions of geology itself. Every glint from that mysterious bright spot is a whisper from the solar system's infancy, a clue waiting to be decoded about how these distant worlds came to be, and why, against all odds, they refuse to fade into the dark. Deep in the Kuiper Belt's frozen expanse, the triple system known as Lempo spins a cosmic riddle, one composed not of a single world, but of three separate bodies locked in an intricate gravitational dance. At first glance, this arrangement seems impossible. Two similarly sized objects, Hisi and Paha, pirouette around a central partner named Lempo, forming a celestial ménage trois that defies the simplicity of most binary systems. What makes this trio so baffling isn't just their delicate balance, but the sheer improbability of such a complex arrangement surviving billions of years in an environment where gravitational disruptions should have torn them apart. Hisi and Paha, each roughly 150 kilometers across, orbit their primary at a distance comparable to Earth's moon, while also circling each other like twinned partners in a never-ending waltz. This nested configuration, a binary system orbiting a larger host, is vanishingly rare, especially this far from the sun's warmth. For such a fragile arrangement to persist, Lempo's family must have formed under unusually gentle conditions, avoiding the violent collisions that typically dominate the Kuiper Belt's chaotic history. One leading theory suggests all three bodies coalesced from the same primordial cloud of dust and ice, their orbits stabilizing before passing comets or planets could disrupt them. Another possibility, Hisi and Paha might have been independent wanderers captured by Lempo's gravity in a cosmic stroke of luck, their velocities perfectly matched to avoid ejection or collision. The real mystery lies in their surfaces. Spectroscopic data reveals all three share nearly identical compositions rich in water, ice, and complex organics, yet Hisi reflects significantly more sunlight than its siblings. This discrepancy hints at hidden activity. Perhaps cryovolcanic eruptions coat Hisi in fresh ice, or its slower rotation allows frost to accumulate in gleaming blankets. Alternatively, Paha's darker hue might come from a shroud of ancient cosmic radiation, suggesting it spent more time exposed to space's harsh conditions. But the most tantalizing clue to Lempo's past comes from its orbit, a stretched, elliptical path that swings it from 38 to 54 astronomical units from the Sun. Such extreme variations should destabilize delicate systems, yet this trio clings together like stubborn survivors. Could their resilience come from an unseen fourth body lurking in the shadows? Or does their very existence force us to reconsider how often such complex families form in the Kuiper Belt's quiet corners? What Lempo teaches us is that even in the sparsest reaches of our solar system, gravity still finds ways to sculpt beauty from chaos. Every observation of this triple system peels back another layer, revealing not just how solar systems form, but how they improvise, turning chance encounters into enduring cosmic ballets. Varda and its moon Ilmari spin through the Kuiper Belt like a celestial pair dancing to a rhythm only they can hear, except this dance has a bizarre twist. Ilmari doesn't orbit Varda in the usual flat, predictable plane like most moons. Instead, it loops around at a dramatic 45-degree tilt, as if someone knocked the system sideways and left it spinning off kilter. This extreme inclination isn't just unusual, it's virtually unheard of for a moon so close to its parent body, defying the neat, orderly patterns we see elsewhere in the solar system. What could throw a moon so violently off course? One compelling theory points to a cataclysmic impact early in Varda's history, where a rogue object smashed into the dwarf planet with enough force to send Ilmari tumbling into its skewed orbit. Imagine a cosmic billiard shot gone wrong, the impactor striking Varda at just the right angle to torque its rotation, leaving Ilmari stranded in this odd gravitational limbo. Supporting this idea are subtle asymmetries in Varda's shape, hinting at ancient scars that could betray such a violent encounter. But there's another, even more intriguing possibility: unseen gravitational meddling. Some researchers suggest Varda and Ilmari might once have been part of a larger, now vanished system, and perhaps even a binary dwarf planet torn apart by a close encounter with Neptune or another massive Kuiper Belt object. As the third body drifted away, its gravitational pull could have yanked Ilmari into this peculiar tilt, like a puppeteer twisting a string before letting go. Alternatively, Varda's own irregular shape, lumpy and oblong rather than spherical, might create uneven gravitational tugs that gradually torqued Ilmari's orbit over billions of years. The most tantalizing clue lies in the moon's composition. Ilmari's surface appears slightly redder than Varda's, suggesting it could be a captured object rather than a fragment born from the dwarf planet itself. If true, this would make their tilted waltz even more miraculous, a chance gravitational embrace that somehow stabilized against all odds. Yet their shared spectral features in water ice and methane complicate that narrative, implying a deeper connection than a random capture event should allow. Why does this matter? Because Ilmar's tilt is a frozen record of the Kuiper Belt's chaotic youth. If impact shaped it, we're glimpsing the violence of the early solar system. If hidden forces are to blame, we might be staring at evidence of lost worlds that once shared this space. Every new observation peels back another layer of this orbital enigma, proving that even in the quietest corners of the cosmos, gravity still has surprises up its sleeve. Among the Kuiper Belt's most enigmatic wanderers, the duo of G-1C, 3Ku acute N-1C, 1 ejective H-ogrov MD-acute-M, and Decode Makemake path so wildly eccentric they seem to defy the gravitational rules of our solar system. These phonetically mesmerizing worlds, whose names hail from the indigenous letter 1, C0's Am language of southern Africa, don't just orbit the sun. They slingshot around it like cosmic comets on steroids, their elliptical trajectories stretching so far into the void that at their most distant they flirt with interstellar space. What makes their orbits truly bizarre isn't just their stretched-out shapes, but their steep tilts relative to the solar system's flat plane, as if someone yanked them sideways and sent them tumbling off kilter. G-1C, 3Ku acute N-1C, 1 ejective H-ogrov MD-acute-MIS path is particularly extreme. At its closest, it ventures nearer to the Sun than Neptune, only to later retreat over 130 astronomical units into the frigid darkness. That's like a celestial pendulum swinging from just beyond Saturn's orbit all the way out to 3 times Pluto's average distance. Such radical swings suggest a turbulent past, possibly a close encounter with Neptune that acted like a gravitational catapult, hurling it into this stretched configuration. But here's the catch: current models struggle to recreate this orbit through Neptune interactions alone. The angles don't quite add up, hinting that another force might be at play. Perhaps the gravitational tug of an undiscovered rogue planet lingering in the solar system's shadows, or even a passing star that grazed our cosmic neighborhood billions of years ago. Decode complicates the story further. While slightly less elongated, its orbit is sharply inclined, tilted nearly 30 degrees from the solar system's plane. This odd angle suggests it wasn't gently nudged but violently upended, possibly by multiple gravitational kicks from different giant planets during the solar system's chaotic youth. Spectroscopic observations reveal another clue. Both objects share a peculiar reddish hue darker than most Kuiper Belt residents, implying their surfaces have been baked by eons of cosmic radiation during their long, lonely treks into the outer darkness. The most tantalizing possibility: these two might be relics of a larger population of extreme objects whose orbits were scrambled by a now-vanished perturber, a hypothetical planet 9 or a since-ejected sibling of Neptune. Their clustered orbital angles could be celestial breadcrumbs tracing back to whatever disrupted them. Yet for all their eccentricity, G-1C, 3Ku acute N-1C, 1 ejective H-ogrov MD-acute-M, and Decode aren't lone rebels. They're part of a growing class of detached objects whose paths suggest our solar system's history was far more tumultuous than we ever imagined. Every new calculation peels back another layer, revealing that even in the frozen fringes, gravity's fingerprints tell stories of chaos, chance, and cosmic billiards on an unimaginable scale. What's clear is that these worlds aren't just oddballs, they're time capsules preserving clues about the gravitational storms that shaped our solar system's architecture. Whether their wild orbits were sculpted by known giants, unseen invaders, or forces we've yet to imagine, their very existence challenges us to rethink how small bodies navigate the gravitational web woven by the universe's invisible hands. Out in the frozen outskirts of our solar system, floating among the Kuiper Belt's icy denizens, 2002 UX25 presents a cosmic paradox, a world that defies the very definition of what a mid-sized object should be. Most Kuiper Belt objects follow a predictable pattern. The bigger they are, the denser their interiors. But UX-25 breaks all the rules, measuring about 680 kilometers across. It's large enough that gravity should have compressed it into a relatively solid mass, yet its density is shockingly low, so low, in fact, that scientists estimate it's nearly 70% empty space. Imagine a celestial sponge the size of Arizona, riddled with caverns and fractures so vast they could swallow entire mountain ranges. How could something so substantial remain so light? One radical theory suggests its interior might be a labyrinth of hollow chambers, carved out by ancient geological processes we've never observed before. On Earth, porous rocks form through volcanic activity or erosion, but UX-25's frigid environment lacks the heat or flowing liquids needed for those mechanisms. Instead, researchers propose that exotic ices like methane or nitrogen clathrates could have sublimated over billions of years, leaving behind a honeycomb of voids where solid material once existed. Picture dry ice vaporizing in reverse, slowly transforming a frozen world into a fragile cosmic skeleton. Even stranger is the possibility that UX-25 never fully collapsed in the first place. Most objects in the Kuiper Belt are thought to be rubble piles, loose collections of smaller rocks held together by gravity. But models suggest something as large as UX-25 should have compacted under its own weight, squeezing out those gaps like a cosmic trash compactor. The fact that it didn't hints at materials with bizarre structural strength. Perhaps ice is reinforced by organic polymers, creating a framework rigid enough to resist gravitational crushing. Or maybe it's not strength at all, but an absence of force. Some simulations suggest UX-25 might have formed in an unusually gentle environment, where collisions were too soft to trigger consolidation. Then there's the wild-card explanation. What if this object isn't a native of the Kuiper Belt at all? Its peculiar density matches some cometary nuclei better than typical Kuiper Belt residents, raising the tantalizing possibility that UX-25 could be an interloper, hurled inward from the even more distant Oort cloud during the solar system's chaotic infancy. If true, its porous structure might be a frozen snapshot of conditions far beyond the planet, preserved in icy isolation for billions of years. But perhaps the most humbling lesson UX-25 teaches us is how little we understand about the middle children of the solar system. We've studied massive dwarf planets like Pluto and tiny pebbles like Arrokoth, but objects in this intermediate range, too big to be simple rubble piles, too small to fully collapse, are proving to be full of surprises. Every new observation challenges our assumptions, reminding us that even in the coldest, darkest corners of space, nature still has a few tricks up its sleeve. Spinning through the Kuiper Belt like a cosmic top gone berserk, 2003 VS2 completes a full rotation every 4 hours, a dizzying speed that should have shredded this icy world into space dust long ago. Picture a snowball the size of a small city whirling so fast its equator bulges outward, fighting against gravity's grip with every passing second. Most objects this size take days or even weeks to spin just once, yet VS2 defies physics with its breakneck pirouette, leaving astronomers scrambling to explain how it hasn't flown apart. One theory points to an interior far stronger than expected. A hidden skeleton of rock or metal lending structural support beneath the icy shell. Imagine a frozen lake with steel cables woven through its depths. Even as centrifugal forces pull outward, that rigid framework might be holding VS2 together like a celestial corset. But here's the catch. Spectral analysis reveals almost no rocky material on its surface, just gleaming water ice and traces of methane. If there's reinforcement beneath, it's buried deep, shielded from view by eons of accumulated frost. The more radical explanation, VS2 could be a cosmic rubble pile held together by icy glue. Instead of a solid mass, it might be a loose collection of boulders and dust, its gaps filled with sluggish, tar-like ice that flows just enough to absorb the stresses of rotation. Think of it as a snow globe packed not with water, but with molasses. Every flick sends the flakes swirling, yet the thick liquid prevents them from escaping. This model suggests VS2 ices aren't brittle, but viscoelastic, stretching and rebounding with each rotation like a stretchy cosmic bandage, keeping the fragments intact. Yet even this idea has its holes. Rubble piles typically form from catastrophic collisions, and VS2 surface shows none of the scars expected from such violence. Its shape, while elongated, lacks the dramatic distortions seen in other fast-spinning objects like Haumea. Could it have formed this way from the beginning, its components gently merging in a slow-motion dance that preserved its fragile structure? The most tantalizing clue comes from VS2 temperature. Unlike most Kuiper Belt objects which radiate heat evenly, this one shows puzzling hotspots near its equator, precisely where friction from its rapid spin should be generating the most stress. Some researchers speculate these warm zones hint at active resurfacing, where internal heat softens the ice just enough to patch stress fractures as they form. Others propose tidal forces from an unseen moon might be subtly flexing VS2 interior, adding energy to keep it spinning against all odds. What makes VS2 so mesmerizing isn't just its defiance of expectations, but what it reveals about the hidden diversity of the Kuiper Belt. Here in the solar system's freezer, where temperatures plunge below -200 degrees Celsius, materials behave in ways we're only beginning to understand. Ice isn't just ice. It can be armor, glue, or even a cosmic shock absorber, adapting to conditions that would shatter the brittle rules of our warmer, saner corner of space. Every new observation of this whirling enigma chips away at our assumptions, proving that even the simplest ingredients, rock, ice, and motion, can combine into something spectacularly strange when the universe decides to experiment. Lost in the frozen darkness of the Kuiper Belt, 2004 AW95 sticks out like a misplaced artifact in an alien museum, a carbon-rich relic that somehow wandered billions of miles from its birthplace near the Sun. This cosmic oddball doesn't belong here. Its surface, stained a deep reddish-black by organic molecules and graphite, screams inner solar system origins, a composition you'd expect from asteroids orbiting between Mars and Jupiter. Yet here it sits far beyond Neptune, a planetary castaway frozen in exile. The evidence lies in its spectral fingerprint. When astronomers first analyzed EW95 light, they found unmistakable dips and spikes matching carbonaceous chondrite meteorites, the same primitive material that formed the building blocks of rocky planets. But the real smoking gun, absorption features indicating phyllosilicates, minerals that require liquid water to form. That's the ultimate paradox. This object must have once been warm enough for chemical reactions with water, only to later freeze solid in the Kuiper Belt's icy waste. So how did a sun-baked world end up in deep freeze? The leading theory points to Jupiter's grand migration. Billions of years ago, as the gas giant lumbered inward toward its current orbit, its immense gravity would have acted like a cosmic slingshot, hurling nearby objects in all directions. Some spiraled into the sun, others were ejected entirely, but a lucky few like EW95 may have gotten just the right gravitational kick to send them careening outward, where they eventually settled into the Kuiper Belt's distant sprawl. Not everyone's convinced. Alternative explanations suggest EW95 might be a rare survivor from an entirely different scenario, perhaps a fragment of a shattered protoplanet that formed much farther out than we thought, carrying prebiotic chemistry into the outer darkness. Or maybe it's evidence of an even wilder idea, that the early solar system was a chaotic marketplace where material from the inner and outer regions traded places freely before settling into today's orderly arrangement. The most tantalizing clue comes from EW95 orbit. Unlike most Kuiper Belt objects, its path is moderately inclined, tilted about 29 degrees from the solar system's plane. This slight skew aligns eerily well with models of Jupiter's migratory throes. as if we're seeing the frozen trajectory of something the giant planet once batted away like a celestial baseball. Yet for all the theories, one question lingers. If Jupiter scattered this object, why aren't there more like it? EW95 remains a lonely outlier, its very existence challenging us to rewrite the story of how our solar system's pieces came to rest. Whether it's a refugee from the asteroid belt or a messenger from a lost chapter in planetary formation, this carbon-coated enigma proves one thing. The Kuiper Belt isn't just a graveyard of icy leftovers, it's an archive of the solar system's most turbulent history, where even the unlikeliest survivors have tales to tell. Sedna doesn't just drift through the Kuiper Belt, it flees from it, racing along an orbit so stretched and lonely it makes Pluto's path look like a suburban cul-de-sac. This reddish wanderer takes 11,000 years to complete a single lap around the Sun, its trajectory arcing so far into deep space that at its most distant, it ventures over 900 astronomical units into the void, so remote that our star would appear as little more than a particularly bright pinprick in an endless black sky. What could fling a world 600 miles wide into such an extreme, isolated dance? One spine-tingling theory suggests Sedna might not have formed in our solar system at all. Its chemical makeup, rich in exotic ices and organic compounds, resembles the building blocks of planets, but its orbit is all wrong for a native of the Kuiper Belt. Some scientists speculate it's a planetary orphan, stolen from another star during a close encounter billions of years ago. Imagine a rogue exoplanet, wrenched from its cradle by gravitational chaos, only to be captured by the Sun's gravity like a cosmic hitchhiker. Supporting this idea is Sedna's peculiar inclination. Its orbit tilts at an awkward 12-degree angle, as if it were yanked sideways by an outside force. But there's another, equally dramatic possibility, the passing star hypothesis. Early in the solar system's history, our newborn sun likely shared its stellar nursery with thousands of siblings. One of these neighbors could have brushed perilously close, its gravity plucking Sedna from a more conventional orbit and hurling it into the deep freeze. Computer simulations show such a flyby could explain not just Sedna's path, but also the odd orbits of a handful of other extreme trans-Neptunian objects. The twist: this hypothetical star would need to have grazed us within 80 billion kilometers cosmically speaking, a near miss. Then there's the elephant in the room, or rather, the potential planet. Sedna's orbit aligns suspiciously with a growing body of evidence hinting at an undiscovered giant world lurking in the solar system's shadows. Dubbed Planet 9 by researchers, this theoretical behemoth could be 10 times Earth's mass, its slow, ponderous orbit subtly herding objects like Sedna into clustered, eccentric paths. The math suggests this phantom planet's gravity would act like an invisible shepherd, steering Sedna into its elongated trajectory over eons. Yet despite years of searching, no telescope has spotted this hidden giant, leaving its existence tantalizingly unproven. The most haunting question Sedna poses isn't just how it got there, but what it means for the solar system's history. Its very existence implies our cosmic neighborhood was far more violent and unpredictable than we once believed. A place where stars could steal worlds, where rogue planets might drift between suns, and where unseen forces still sculpt the fates of distant icebound wanderers. Every observation of this frosty outcast doesn't just challenge our models, it forces us to confront how little we truly understand about the chaos that shaped our corner of the universe. Tucked away in the solar system's frozen fringes, 2015 TG-387, nicknamed the Goblin for its Halloween discovery, whispers tantalizing clues about forces we can't yet see. This faint, pinkish world follows an orbit so exaggerated it spends most of its 40,000-year journey lingering in near-total darkness, its elongated path stretching so far that even at its closest approach, it never ventures nearer to the Sun than twice Pluto's average distance. But what makes the Goblin truly remarkable isn't just its extreme trajectory, it's how eerily its movements align with a pattern that could point to the solar system's most controversial missing piece, Planet 9. The Goblin's orbit isn't just stretched, it's clustered. Alongside Sedna and a handful of other extreme trans-Neptunian objects, its farthest point tilts in roughly the same direction, like cosmic compass needles all pulled toward an invisible magnet. This odd alignment defies randomness. Statistically, these orbits should point every which way unless something massive, perhaps 5 to 10 times Earth's mass, is herding them. Picture a shepherd dog subtly guiding sheep, not with barks, but with gravitational nudges so gentle they take millennia to unfold. The Goblin's path, when traced backward in simulations, swings precisely where such a hidden world's influence should sculpt it, adding one more day to point to a celestial conspiracy theory that's dividing astronomers. Then there's the mystery of its color, a pale pink blush unlike the deeper reds of most Kuiper Belt objects. This hue suggests a surface rich in organic molecules called tholins, forged when methane ice gets bombarded by cosmic radiation over eons. But here's the catch: the Goblin's pink is peculiarly muted, as if something, maybe cryovolcanic resurfacing or seasonal frost cycles, has diluted its crimson stains. One provocative theory suggests this world might originate even farther out than we thought, perhaps from the inner Oort cloud, where the sun's feeble light couldn't fully bake its surface into darker compounds. If true, the Goblin could be a rare bridge between the Kuiper Belt and that vast, uncharted reservoir of icy bodies surrounding our solar system. Yet the most haunting question remains: is the Goblin's orbit a cosmic breadcrumb leading to Planet 9, or just a statistical fluke? Skeptics argue that observational biases, our telescope's limited reach, might make these clustered orbits appear more significant than they are. Others counter that each new discovery, like the Goblin, tightens the noose around the Planet 9 hypothesis, turning what was once fringe speculation into a puzzle too precise to ignore. Until we spot that hypothetical giant or rule it out entirely, this pinkish cipher will keep astronomers awake at night, wondering if they're glimpsing the fingerprints of a ghost world, or the limits of our own understanding. Far beyond the bustling activity of the inner solar system, two ghostly worlds drift in slow motion: 2013 Phi 27 and 2014 US 224, a pair of distant twins locked in a cosmic waltz so leisurely it would make glaciers seem impatient. These frozen relics take centuries to complete a single orbit around the Sun, their paths stretched so wide that even at their closest approach they remain shrouded in perpetual twilight. Yet what makes them truly fascinating isn't just their isolation, it's their eerie similarity to one another, as if carved from the same icy blueprint. At first glance, these two could be mistaken for siblings. Both measure roughly 600 to 700 kilometers across, large enough to qualify as potential dwarf planets, and both wear the same reddish coats of tholins, those complex organic molecules that stain Kuiper Belt objects like cosmic rust. Their surfaces reflect sunlight in nearly identical ways, suggesting compositions rich in water ice laced with methane and nitrogen frosts. Even their orbits share an odd kinship, tilted at angles that set them slightly askew from the solar system's orderly plane, as if they'd been gently nudged out of alignment by some long-forgotten gravitational hand. But the real mystery lies in their origins. Are we looking at primordial survivors, icy time capsules that have drifted unchanged since the solar system's infancy? Or could they be the shattered remnants of something far larger, fragments of a lost dwarf planet torn apart by an ancient collision? The case for primordial relics hinges on their slow, undisturbed orbits. Unlike objects that have been jostled by Neptune's gravity, these twins seem to have coasted quietly in the outer darkness for billions of years, their surfaces preserving pristine chemistry from the solar system's earliest days. Yet the alternative theory holds its own intrigue. Their similar sizes and compositions hint at a violent past. Perhaps they're two of many pieces from a catastrophic breakup, siblings in a much larger family now scattered across the Kuiper Belt. If true, their parent body must have been substantial, possibly rivaling Pluto in size before whatever calamity shattered it. Supporting this idea are subtle variations in their rotation rates. FY27 spins once every 12 hours, while UZ224 takes nearly 30 discrepancies that could reflect the different ways they were flung apart in that hypothetical collision. Then there's the wild card, their temperatures. Both objects are colder than expected for their distances, as if their surfaces are somehow insulated against the feeble warmth of the distant sun. One explanation suggests their reddish Tholin coatings might act like cosmic blankets, trapping what little heat they absorb. Another possibility, internal heat retention from radioactive decay, hinting at rocky cores buried deep beneath the ice. If so, these quiet worlds could be more geologically complex than their frozen exteriors suggest. Whether they're untouched relics or cosmic shrapnel, FY27 and UZ224 offer a humbling lesson about the Kuiper Belt's quiet diversity. Even in this realm of ice and darkness, where time moves at a crawl and sunlight is a distant memory, no two worlds are exactly alike. Yet some share bonds that whisper of shared histories written in orbits and ice. Every new observation peels back another layer, revealing that the solar system's farthest reaches still guard secrets we've only begun to decode. 2002 TX300 glows like a dying ember in the Kuiper Belt's darkness, an anomaly so red it makes Mars look bland by comparison. This mysterious world reflects barely 18% of the sunlight that touches it, a baffling trait for an object whose surface should gleam with fresh ice. Most bodies in this region bounce back far more light. Pluto's icy plains reflect up to 60%. So why does TX300 absorb so much? The answer might lie in a cosmic paint job gone horribly wrong. Tholins, those complex organic goos formed when methane and nitrogen ices get zapped by cosmic radiation, are the prime suspects. On other Kuiper Belt objects, these reddish-brown gunk layers are diluted by brighter ices, creating a mottled appearance. But TX300 seems to have dipped itself in the stuff, its surface utterly saturated with tholins so thick they swallow light like a sponge. One theory suggests this world might have started with an unusually high methane content, its icy crust baking under eons of radiation until every last molecule transformed into dark, light-hungry sludge. Then there's the space weathering angle. While most Kuiper Belt objects get occasionally resurfaced by impacts or frost cycles, TX300's slow rotation, once every 8 hours, means each patch of its surface bakes in the faint sunlight for extended periods. Over billions of years, this relentless exposure could have cooked its ices into an ultra-dark crust, much like how a marshmallow left too long over a campfire chars into a blackened shell. Spectroscopic data reveals another clue. While water-ice signatures are present, they're suspiciously weak, hinting that the Tholin blanket might be so dense it's masking the ice beneath entirely. But the plot thickens when we compare TX300 to its orbital siblings. This object belongs to the Haumea family, a group of icy fragments thought to have broken off from a colossal collision. Most members share Haumea's brilliant crystalline ice surfaces, except TX300. Its freakish redness implies either a radically different composition from its cousins or some post-collision process that altered it uniquely. Could it have wandered through a cloud of interstellar dust, picking up a dark coating like a car driving through mud? Or did internal heat, perhaps from radioactive decay, once liquefy its subsurface layers, allowing heavier, darker compounds to rise and congeal on its surface? The most tantalizing possibility, TX300 might not be a true member of the Haumea family at all. Its orbit aligns closely enough to suggest a connection, but its chemistry screams outsider. If confirmed, this would make it an interloper, a rogue world that drifted into the clan's gravitational sphere and adopted their orbital rhythms while keeping its own dark secrets. Every new observation peels back another layer, revealing that even in a realm governed by ice and shadow, the universe still finds ways to defy expectations with something as simple as color. 2007 JH43 drifts silently through the Kuiper Belt, a cosmic loner in a neighborhood where companions are the rule rather than the exception. This 600-kilometer-wide world stands out not for what it has, but for what's conspicuously missing: moons. Nearly every object of comparable size in this distant realm hosts at least one satellite, from Pluto's entourage of 5 to Haumea's pair of dancing partners. Even smaller Kuiper Belt objects often have tiny moons clinging to them like cosmic sidekicks. Yet JH43 orbits in solitary silence, and that absence speaks volumes. One possibility is that this world once had moons but lost them to the Kuiper Belt's violent past. Imagine a catastrophic collision billions of years ago, where an impactor struck JH43 with such force that any orbiting companions were either vaporized or sent careening into the void. We see echoes of this scenario in other systems. Neptune's moon Triton, for instance, was likely captured after a brutal gravitational disruption ejected its original siblings. But JH43's surface tells a conflicting story. Unlike fractured worlds such as Haumea, which show clear signs of past smash-ups, JH43 appears relatively smooth, lacking the cratered scars or elongated shape typical of a violent history. If it did lose moons, the event left surprisingly few fingerprints. Then there's the quieter but no less intriguing alternative. Maybe JH43 never had moons to begin with. While most large Kuiper Belt objects form with companions, their creation depends on specific conditions, gentle collisions in the early solar system that leave debris in stable orbits. If JH43 formed in a sparser region of the primordial disk, where fewer smaller bodies orbited nearby, it might have avoided accumulating lunar partners altogether. Alternatively, its composition could have played a role. Objects rich in volatile ices like methane tend to be less dense, making it harder for their gravity to hold onto moons after impact. Spectroscopic observations hint that JH43's surface is unusually rich in these lighter compounds, potentially explaining its solitary nature. The most tantalizing clue lies in its orbit, a nearly circular path that keeps JH43 steadily distant from Neptune's gravitational reach. Unlike many of its peers, this world hasn't been jostled by close encounters with giants, leaving its history remarkably undisturbed. That stability might be the key. Moons often form or are captured during chaotic gravitational interactions, so JH43's serene journey could have denied it the turbulence needed to acquire companions. Yet the mystery deepens when we consider another strange trait: JH43 rotation. While most solitary objects spin rapidly, their angular momentum unchecked by orbiting partners, this world rotates at a leisurely pace, completing a full turn every 18 hours. That sluggish spin defies expectations, suggesting unseen forces once braked its motion, perhaps the ghostly tug of long-lost moons that spiraled away over eons, or residual effects from a primordial magnetic field that has since faded. Whether it's always been alone or quietly mourns lost companions, JH43 challenges our assumptions about how celestial families form. Its moonless existence forces us to reconsider the delicate balance of chance, chemistry, and chaos that determines whether a world becomes a parent, a partner, or a solitary wanderer in the dark. 2005 QU182 doesn't just orbit the Sun. It practically ricochets around it, swinging from 38 to 110 astronomical units in a cosmic pendulum swing so extreme it leaves astronomers scratching their heads. This wandering dwarf planet carves a path through the Kuiper Belt like a celestial pinball, its stretched-out trajectory hinting at a violent past where gravitational forces played pinball with its destiny. What could slingshot an object nearly 1,000 kilometers wide into such an erratic dance? The prime suspect, Neptune's restless adolescence. During the solar system's chaotic early days, Neptune didn't stay put. It migrated outward, bulldozing through ancient debris fields like a gravitational snowplow. As it inched away from the Sun, its colossal gravity would have hurled smaller objects in all directions, some inward, some outward, and a few, like Quaoar, into bizarre, looping orbits. Simulations suggest this dwarf planet might have been caught in a game of gravitational hopscotch, bouncing between resonant interactions with Neptune and other giants until it settled into its current stretched configuration. Imagine a cosmic billiards shot where each planet's gravity adds another unpredictable nudge, sending Quaoar careening farther into the void. Yet Neptune's influence alone doesn't fully explain the sheer scale of Quaoar wanderings. Its orbit tilts at a sharp 19-degree angle as if something or someone gave it a sideways kick along the way. That's where the rogue planet theory slithers in. Some researchers speculate Quaoar path aligns too perfectly with hypothetical gravitational disturbances from an unseen ninth planet, its ghostly tugs warping orbits over billions of years. Others propose a more dramatic past, a close encounter with a passing star in the Sun's birth cluster, a gravitational handshake so fleeting yet so powerful it left Quaoar permanently off-kilter. The real enigma lies in Quaoar surface. Unlike many Kuiper Belt objects stained reddish by tholins, this wanderer reflects sunlight with a peculiar grayish hue, suggesting a crust stripped of volatile ices or coated in exotic minerals. One theory posits its wild orbital swings expose it to extreme temperature shifts, baking away methane and nitrogen frosts over eons and leaving behind a barren, rocky veneer. Alternatively, its grey pallor might betray an origin story far from the Kuiper Belt, perhaps a refugee from the scattered disk or even the Oort cloud, its chemistry forever altered by the journey. What makes Quaoar so mesmerizing isn't just where it's been, but where it's headed. Current projections suggest its orbit is still evolving, subtly reshaped by unseen forces. Will it eventually stabilize, or is it destined to be ejected entirely, becoming a free-floating interstellar nomad? Every observation of this cosmic drifter peels back another layer of the solar system's turbulent history, a reminder that even in the frozen quiet of deep space, gravity's fingerprints tell stories of chaos, chance, and celestial wanderlust. At the solar system's outermost edge, so distant that sunlight takes over 2 days to reach it, 2018 VG18 drifts through the void like a cosmic ghost. Nicknamed Far Out by its discoverers, this pink-tinged enigma holds the record as the most remote object ever observed orbiting our Sun, its languid path carrying it over 120 astronomical units into the abyss. At that staggering distance, the Sun is reduced to a mere speck, its light so feeble that Far Out's surface temperature hovers just 40 degrees above absolute zero. Yet what makes this world truly remarkable isn't just its isolation, it's the cryptic forces that may have exiled it there. That delicate pink hue offers the first clue. Unlike the deeper reds of many Kuiper Belt objects, Far Out's pastel tint suggests a surface rich in exotic ices, likely methane or nitrogen, that's been gently cooked by cosmic radiation into rosy-hued tholins over billions of years. But here's the twist, its color isn't uniform. Patches appear brighter than others, hinting at active processes refreshing its frosty crust. On a world this cold and distant, where even gases freeze solid, what could possibly be resurfacing it? One radical theory points to seasonal outbursts, pockets of subsurface gas warming ever so slightly during Far Out's rare close approaches to the Sun, enough to erupt in sluggish geysers that dust its surface with fresh, reflective frost. Then there's the puzzle of its orbit, a slow-motion ellipse so stretched it takes over 1,000 years to complete a single lap around the Sun. Most objects this far out follow paths shaped by Neptune's gravitational nudges, but far out's trajectory aligns suspiciously with a pattern that's become all too familiar to astronomers: the possible influence of an undiscovered giant planet. Like Sedna and the Goblin, far out's farthest point clusters mysteriously in one sector of the sky, as if an unseen hand has gently guided it there. The math suggests something massive, perhaps 5 to 10 times Earth's mass, lurking hundreds of astronomical units away, its gravity subtly herding these distant wanderers into coordinated paths. Yet the most haunting question isn't just where far out is going, but where it came from. Its chemistry suggests it formed much closer to the Sun, where temperatures allowed volatile ices to accumulate before some cataclysmic event. A close encounter with Neptune, a rogue star's gravitational brush, flung it into the deep freeze. Alternatively, it might be a rare visitor from the inner Oort cloud, a region so distant and dim we've never directly observed its inhabitants. If true, far out could be a messenger from a reservoir of primordial objects untouched since the solar system's birth, offering clues about the raw materials that built our cosmic neighborhood. What humbles scientists most is how little we truly know. Far out's discovery in 2018 was accidental, spotted during a survey for other distant objects, proof that even our most powerful telescopes are barely scratching the surface of what lies beyond. Every new pixel of data reveals another layer of mystery, from its inexplicable brightness variations to the way its slow spin defies models of icy body rotation. In this frozen realm where the rules of physics bend under extreme conditions, far out stands as both a milestone and a taunt, the farthest known member of our solar system's family, and a reminder that the real frontier of discovery still lies ahead, waiting in the dark. The Kuiper Belt keeps tossing cosmic curveballs our way, each mystery peeling back another layer of how little we truly understand about our own solar backyard. Take rings, those elegant halos we once thought were the exclusive domain of gas giants like Saturn. Finding them around small, icy bodies like Quaoar and Haumea appends centuries of planetary science. Conventional wisdom says rings should only form within the Roche limit, where a moon would be torn apart by tidal forces. Yet Quaoar's ring floats defiantly outside that boundary, a fragile loop of ice and dust surviving against all odds. Could hidden moons shepherd these particles, their gentle nudges keeping the debris in line? Or are we witnessing the aftermath of a collision so precise, it left debris suspended in a perfect balance between gravity and momentum? The implications ripple outward. If rings can exist in these unlikely places, how many other small worlds might be hiding similar secrets? Then there's the palette of the Kuiper Belt, a cosmic art gallery where no two canvases look alike. Some worlds gleam like frosted mirrors, their surfaces fresh with crystalline ice. Others are stained dark as coffee grounds, shrouded in tholins baked by eons of radiation. What separates a cherry-red Sedna from a pale pink Goblin, or a charcoal-black TX300 from the rosy blush of far out? The answer might lie in a celestial tug of war between chemistry and chaos. Objects rich in methane, like Eris, transform into crimson time capsules when radiation cooks their surfaces. But others, like Haumea, spin so fast they constantly renew their frosty exteriors, polishing themselves like self-cleaning cosmic ornaments. And what about those baffling bright spots, Makemake's gleaming patches or Arrokoth's crimson sheen? Are they cryovolcanic frost, impact-exposed ices, or something far stranger? The variations aren't just skin-deep, they're fossilized records of each world's unique history, written in a language of light and shadow we're only beginning to decipher. But perhaps the most tantalizing question hangs over the Kuiper Belt like a phantom. How many undiscovered dwarf planets still lurk in the dark? We've catalogued fewer than a dozen, yet simulations suggest dozens. Even hundreds might be hiding just beyond our telescope's reach. The math is humbling. When astronomers spotted distant, slow-moving far out, they weren't even looking for it. Its discovery was pure serendipity, a reminder that our maps of the outer solar system are still dotted with "here be dragons." And then there's the elephant in the room, Planet 9. The odd clustering of orbits from Sedna to the Goblin hints at something massive shepherding them, a hidden giant whose gravity could rewrite the Kuiper Belt story. Yet year after year, searches come up empty. Is it a super-Earth cloaked in darkness, a black hole masquerading as a planet, or merely a statistical mirage? Until we find it or rule it out entirely, its ghostly presence lingers over every unexplained wobble and odd trajectory. What ties these mysteries together is their defiance of neat categories. The Kuiper Belt isn't just a relic of the past, it's a dynamic, evolving frontier where conventional rules crumble. Rings defy orbital mechanics, colors shift like cosmic mood rings, and unseen giants may still be waiting in the wings. Every answered question breeds three more, proving that even in the frozen quiet of deep space, the universe refuses to sit still. Staring into the Kuiper Belt's abyss isn't like pointing a backyard telescope at Jupiter. These frozen worlds are so distant and dim. Spotting one is like trying to read a street sign through fog from 50 miles away. The faintest objects reflect less light than a single snowflake under a full moon, forcing astronomers to deploy every trick in the cosmic playbook just to catch whispers of their existence. Take adaptive optics, for instance, a game changer that turns Earth's turbulent atmosphere from an obstacle into an ally. By firing lasers into the sky to create artificial guide stars, telescopes like the Keck Observatory in Hawaii can measure atmospheric distortion in real time, then bend their mirrors 1,000 times per second to cancel out the blur. It's like giving cosmic spectacles to a ground-based telescope, sharpening its vision enough to pick out a city-sized ice ball 4 billion miles away. But spotting these objects is only half the battle. Mapping their orbits requires patience bordering on obsession. While inner planets zip around the sun in months or years, Kuiper Belt objects creep along paths spanning centuries. A single orbit for something like Sedna takes longer than all recorded human history, meaning astronomers must stitch together glimpses separated by decades to trace their trajectories. That's where archival images become time machines. By digging through old photographic plates and digital sky surveys, researchers have caught slow-moving dots missed in original scans, like finding a hidden frame in a cosmic flipbook. The discovery of Eris in 2005, it was lurking in images taken back in 1954, invisible until someone knew where and how to look. Then there's occultation tracking, nature's own cosmic detective tool. When a Kuiper Belt object passes in front of a distant star, it casts a shadow so fleeting, often less than a second, that catching one requires military-grade coordination. Teams deploy telescopes across continents, waiting for that precise moment when the object's silhouette briefly dims the star's light like a celestial eyelid blink. From that split-second dip, scientists can calculate the object's size, shape, and even whether it has an atmosphere. In 2017, this method revealed rings around Haumea before any spacecraft could visit, proving you don't need to travel billions of miles to uncover secrets, just impeccable timing and a globe-spanning network of observers. The real unsung heroes, though, are the infrared and radio telescopes. Since many Kuiper Belt objects glow brighter in heat signatures than reflected sunlight, instruments like the James Webb Space Telescope can peer through the darkness by tuning into their thermal whispers. By comparing an object's infrared warmth to its visible light dimness, researchers can deduce surface properties, whether it's covered in dark, heat-absorbing tholins or bright, reflective ice. Meanwhile, radio telescopes like ALMA in Chile pick up millimeter-wave emissions, revealing subsurface chemistry without ever leaving Earth. It's cosmic forensics, where every wavelength tells a different part of the story. Yet for all this technological might, the Kuiper Belt still guards its secrets jealously. Signals from these distant worlds are so weak that a cell phone on Pluto would appear 10,000 times brighter than the objects we're trying to study. That's why missions like New Horizons are irreplaceable. Flying by Arrokoth in 2019 gave us crisp details no Earth-based observation could match, from its pancake lobes to its crimson stains. But with travel times measured in decades and targets scattered across billions of miles, we've only scratched the surface. Upcoming telescopes like the Vera C. Rubin Observatory promise to discover hundreds more, each a new piece in the puzzle of our solar system's birth, if we're willing to keep staring into the dark, waiting for the next faint flicker of discovery. From Arrokoth's delicate cosmic snowman shape to Haumea's improbable rings, from Quaoar's defiant distant halo to Sedna's lonely interstellar orbit, each of these 25 Kuiper Belt objects forces us to rewrite the rules of planetary science. These aren't just frozen relics, they're rebels, outliers that laugh at textbooks. Who imagined rings could survive outside the Roche limit, or that a world like Gong Gong could tilt its orbit like a stubborn child refusing to fall in line? The Kuiper Belt was supposed to be a quiet graveyard of icy leftovers, but instead, it's a chaotic laboratory where dwarf planets spin faster than should be possible, where carbon-rich asteroids teleport from the inner solar system, and where ghostly rings and undiscovered giants might still lurk in the shadows. Consider the impossible contradictions. Eris gleams brighter than fresh snow, while TX300 swallows light like a black hole. Lempo's triple system dances in perfect harmony, while the Goblin's orbit points to an unseen puppet master. Some, like Makemake, wear bright patches like cosmic makeup. Others, like 2002 UX25, are hollowed-out skeletons defying gravity's crush. And then there's far-out pink, pristine, and so distant it feels less like a member of our solar system and more like a message in a bottle drifting in from the void. Every discovery peels back another layer of our ignorance, proving that the outer solar system isn't just stranger than we imagined, it's stranger than we can imagine. This is the frontier of human knowledge, where every answer sparks 3 new questions. So tell us, which mystery grabs you? Is it the enigma of Planet 9, the riddle of Haumea's spin, or the haunting beauty of Sedna's exile? Drop your thoughts below and keep looking up. The universe isn't done surprising us yet.